Welcome to Rohde Electronics Labs. And recently I posted two videos about doing FFT analysis on oscilloscopes. And in the last of the two videos I've been talking about a mystery that we got into when it came to the Rohde Schwarz RTB oscilloscope doing FFT measurements. And that mystery basically had two parts to it. The first part is that we don't seem to know for sure whether the parameters that we see on the screen are the actual parameters used for the FFT process. And that is important because if you don't know what the actual settings in the oscilloscope are, you can't know for sure whether what you're seeing on the screen is actual signals that you're analyzing or, for example, aliasing effects. So you really need to know, for example, what the actual sample rate for the FFT process is, so you can decide whether a given input signal can or cannot be analyzed given those conditions. And the second mystery was how the parameters showed by the RTB oscilloscope compared to what we would expect to see from the theoretical relationship between the various FFT parameters. Now, in today's video, I'm going to go in depth into further experiments with the Rohde Schwarz RTB oscilloscope, and we will see today that the first mystery is largely solved, but the second mystery is even a bigger mystery than before. So let's get started and look at those two things in particular that I talked about, which is about the whether the parameters we see are the real parameters and how they relate to the theoretical relationships that we should expect to see. Now let's quickly refresh our mind what aliasing exactly is. And to do that I'll use this little picture, this little animation that is available on Wikipedia, and I think it's very nicely made. So let's quickly just take a look at it. I'm going to play the animation here. And so what we see is a frequency of increasing, a signal of increasing frequency. I'm going to hold it right here. Yeah, and so this is being sampled, this frequency. So we see here in blue the blue dots are the sampling point basically. This is the ideal frequency domain representation that we would get. And down here in orange we see again the sample dots and the reconstructed waveform by FFT. And the frequency domain as we would see it from the FFT analysis. And at this particular frequency that we're looking at, everything is still looking perfectly well, because if we take here these dots, like the sampled values, we can exactly reconstruct here the signal that we're looking at. And I'm also assuming here that the oscilloscope or the spectrum analyzer with FFT or the computer is basically showing the reconstructed frequency spectrum up to half the sampling frequency, also called the Nyquist frequency, because that is the maximum signal that you're supposed to be allowed to sample given a sample frequency of Fs. Yeah, and that's why I inserted this gray box over here. Now I will start again the animation and take a close look what happens at the moment that the original input frequency gets above the Nyquist frequency. So here we go. It's at the Nyquist frequency, it's now above the Nyquist frequency, and now actually we see here a signal going to the left side and going down. I'm going to hold it again. So what has happened basically? The input frequency here is above the Nyquist frequency. Again we see here the sampled points that we got, and we see them down here as well. But if we don't know what the original waveform here and we just have these dots here, the sampled value, we can just as well reconstruct the orange wave that we see down here. This doesn't really exist, of course, this wave, but that is what we will be able to reconstruct if we would offer a signal that is higher than the Nyquist frequency, which would normally not like to do. And so that's why we get here this value here, which is actually going further down if we further increase the frequency. Yeah. So normally we would not like that to happen. So normally we would take measures to prevent that from happening, either by simply choosing not to sample frequencies that are higher than half the sample frequency, the Nyquist frequency, or by adding like an analog filter before the sampling process that will prevent that from happening, or using oversampling or some other measures that you take. But today in my video I'm actually gonna take the side effects of aliasing actually as a tool, because they are predictable in nature, and actually by means of this predictability we can learn some interesting things about what's happening inside the RTB oscilloscope. Good, so now we're turning to the oscilloscope, and I have put on the FFT function, and I'm showing now 0 to 1 megahertz spectrum. Yeah, so the center is 500 kilohertz and the span is 1 megahertz in total. And I will start by feeding a signal into it. I do that with the signal generator, which is above the scope. Let me zoom out a little bit so we can see that happening. And I prepared there a tone of 550 kilohertz that we should see slightly above the middle here. And that's what's happening right now. Okay, this is what we expect to see. Now what I'm going to do is to create a second tone, and with the second tone actually I'm not going to be worried about aliasing, but actually I'm going to exploit the fact that aliasing is taking place. So how do I create a second tone that goes into the oscilloscope? Well, I will do that by actually combining the two output signals of the signal generator. This is a rather useful option. We can go to an output setup menu, and we can do waveform combine, and there we have different options to combine things, and actually I'll make sure that output 1 is actually a addition of the two channels of the device. So I'm switching to channel number 2 here. I set channel number 2 at 1 kilohertz tone, and we already do see that tone coming in. So this is all still what we would expect to see. Now let's go and play with the tone at channel 2. So I'll increase it in frequencies by step of 100 Hertz. So we see it going up. We see it jumping over the other tone, the other tone of 550. So we're jumping from 500 to 600 here. We go up, and now we come at the point that our tone is disappearing from the view, because we're only looking to 1 megahertz and we're feeding in 1 megahertz now. But I'll continue, and for a while we're not going to see anything at all. And now I keep on increasing, but you see, I see a tone coming back, but it goes in the opposite direction. So I'm going to put that tone at 2.1 megahertz. So what I'm seeing is this is exactly the aliasing effect, because I can see that my sample frequency is 2.5 megahertz. I'm feeding in a tone of 2.1. I should be expecting to see the sum and then the subtraction frequency, and exactly 2.5 minus 2.1 will be 400 kilohertz, and you see that tone is exactly at 400 kilohertz. So by doing this, basically I am confirming now that the sample frequency of the FFT procedure is indeed the 2.5 mega samples per second we see here. So this is not only the time-based setting, but now I know this is actually the current FFT setting. And that was the big question we were having, because earlier we were wondering where actually the sampling frequency, and thus also the Nyquist frequency for the FFT mechanism, would be perhaps different in some settings from the time domain ADC settings, and that would explain why we were having that mystery. But now I know for sure that in this particular setting it is the same. Now, whether it is always the same, we could test that by actually go to the FFT function and playing around with the resolution bandwidth. So if we put the resolution bandwidth on automatic, well, we still see we see different resolution bandwidth, but we see our two tones still at the same position in the spectrum. If I turn it to manual control, then I can set the bandwidth myself, and I'll go to the most extreme settings. I'll go to the smallest setting. There we see very narrow tones, but they're still exactly at the same position. If I go to real-time, to resolution bandwidth, and I go to the most extreme maximum setting, so we're going to see very broad lobes. Yeah, we see that, and it's still exactly at the same spot. We see a slight change of of sampling frequency from 2.5 to 2.55. Must be a reason for that, but that's fine. So now we know that whichever setting we take, and I tested this also for a number of other frequencies and setting, the sampling frequency and thus also the Nyquist frequency that we see here on the screen is exactly what's being used for the FFT analysis. And this is good news. At least that makes the whole process a bit more predictable. Now we know, given a certain input signal that we want to analyze, whether the scope is able to properly show it, or whether we should be worried about actually seeing alias type of effect instead of real things. It's still not super convenient that we cannot manually set here the band of the sampling frequency setting, but at least we got a bit more understanding of what is happening in the process right now. Now we solved that first part. Let's go to the second part of the question we were having, and that is like all the FFT parameters and how that relate to what we would expect them to be. And just recalling the two formulas that I discussed in the earlier video, which is what the expected bin width is, the sample frequency divided by n, which is the number of FFT points, and the resolution bandwidth, which is a k factor times the value of bin width, where k is one of these values. Now this is discussed in detail in the previous video, so I'm not going to go in further detail there. You can take a look at it there. Now, so the last time we were struggling a little bit to see all these values, what's happening inside the RTB scope. But actually, as some people have pointed out on the EEV blog in reply to my videos, some of these values can actually be figured out when you start to use the command line interface of SCPI, called also Skippy, I understand, so that's how I'll be pronouncing it today, and that actually gives us a much richer set of details. And there are like over 110 different Skippy commands related to FFT available on the RTB scope, but here I'm showing the ones that I'm basically interested in for our analysis today. And most of them can be found in the documentation of the device, but I'm also going to talk about a couple of commands here that are undocumented for the RTB scope, but they've been found by other people and shared on the internet, and sometimes they actually exist on other Rohde and Schwarz devices, and they just happen to work on the RTB if you try so. I was also looking at the manual of another Rohde and Schwarz device, the Scope Writer R2H, and it actually has a command that queries the sample rate of the FFT analysis. So maybe in this device the FFT sample frequency is not always the same as the time domain sample frequency, but that's mere speculation. This particular command is not supported by the RTB. Quickly going through those here. So first of all, we got a command that actually tells us about the real number of FFT points that is being used in a given analysis, which is super useful. We got an analysis that gives us the bin width, and I'll refer you to the documentation of the oscilloscope where they describe all of this, how it is to be interpreted. I'm not going to put it all down here on the screen. We got the sample rate, which is the time domain sample rate that I was just talking about in the previous part of the video. And actually, if we use another command there, we get to see the same thing, but in a slightly higher resolution, which is useful. Then we got a command which is a header. It delivers 4 values. Unfortunately, that is not very clearly documented. The second value seems to be always half of the FFT frequency, so I assume it's a Nyquist frequency, but it's not documented. And the other value is the number of FFT points, as we saw before. Then there are 2 values. Simply the one is typically 0 and the one is typically 1 when I read it out. I have no idea what they mean. There's a parameter which is called the data points, and that's the record length. But as we will see in a moment in the video, that's a number which I also previously in the video showed that was shown on the screen, but better to be ignored altogether. There's the value where the resolution bandwidth is being set, can be set both as an absolute value or in a ratio of the span. There's also a function basically to read out or to change the Windows function that is being used, and there's a function that actually can tell you the factor that is associated with that Windows window is being in use there. Now to test the different settings on the device, I will be using the web interface, and I'll bring that into the picture now. So this is the web access interface that we saw before of the Rohde Schwarz scope, and among other things we have here the remote front channel, front panel, where we got like all the different controls that we can be using here, as well as the live screen, which has a fairly quick screen update. I don't know how it's going to look exactly in the video, but it's fairly quick. So we also got other parts in the web interface. Actually, I'll bring up a second version of the web interface, and I'm going to put it right here just next to it so we can see both. And I'm going to go to the Skippy device control here. And so the nice thing is that actually in order to use these commands, we don't have to install things like device drivers or the whole set of National Instrument drivers, etc. to make this working. We can just do it right away from the web interface. Now I'm going to give a little demonstration of that. Let me just go back to the front panel and activate the FFT setting. So we see now we are on the flat top window. Now in order to change that window, I can decide to change that window to for example the hum window. So I'll go here. Just typing that in, and you will see that the screen has changed and it goes to the Hemming window. We can use the command that actually confirms to us in the code what window it has selected. So that is the one with the question mark. So we see Hemming window, and interestingly we can see the factor that is associated with the factor command. So there we got it. So we can also run all three of them in one set, and there we go. So we change it to Hemming, we ask what it is, and it is Hemming, and we see the factor with it. Actually you can run all these different windows and look at their factors on the device. I will now bring it back basically to the flat top what I had before, and actually we see back here in the web interface it's on flat top. I'm choosing flat top for my experiments here because it got the largest factor 3.84, so it's easier kind of to do the formula to really see the proper setting. That's the only reason I'm choosing it right now, not because of particular properties, but just because of the FFT formula that I would like to explore. Now these settings basically show here the 3.84 what the RTB considers the bandwidth factor. I don't really mind so much what the exact one is. Some maybe have other ideas about the effect, but I do like that I can have the device telling me what factors is, so I can actually replicate the calculations and know what number that the RTB will be plugging in there. Actually, if we look at all the numbers for the different windows supported on the RTB, we get the ones that we see here on the screen. So they're not exactly identical to the one that I showed in the previous video, which came off the internet, but so we don't care really what the exact setting is, but it's great to know the precise values that the RTB is using in its settings. Now, basically, I want to use now this command line interface to run through a number of different scenarios, like a large number of different scenarios. So I want to change the bandwidth setting, and I want to read like all these parameters that we were just looking at in some of the previous sheets, and see if we can recognize values. Now I could run them all one by one, that would take a lot of time, but we just saw we can run multiple of them at the same time. So I'm actually going to add here a set that I've prepared in advance, and this is going to do a query for something like 10 commands in a row. So this is the one for the resolution bandwidth of 100 Hz. So I'm running it and we see the picture changing, and so we get all these different values that we're interested here in one run, and we can of course take them out and process them. And in a similar way, you know, can make a similar set of commands like that for 28 kilohertz. I'm going to do that right now. I'm going to send it, and we see actually different numbers. You might have seen here that here the screen has changed, and we also see 65,000 here, 64K So that's probably the number of bins that we're using. So this is a convenient way actually to test a large number of settings on the device. And with the experience that I showed you, I actually run a fairly large number of values through there in a semi-automated way. So what I did is that I wrote an Excel sheet that actually prepares the command that I'm parsing in, and then I'm reading out the results. Of course, basically this type of language would also be able to completely automate the process. So I could also have gone and write a routine that would have automatically done all of that without using the web interface. But I think for the task at hand, that was simply faster still to do it in this semi-automated way. So I did so for a series of over 100 calculations. I think it's 127 in total, and each time I'm reading out here these different values that I'm interested in, and I did a number of checks as well on the values just to make sure there were no errors down in that process. And let's now move at what we actually get to see if we try to use these earlier formulas on this. Because now we actually get from this data the number of FFT points, we got the sampling frequency, we got the factor, so we can all try to calculate that now. And so I did it in a number of steps, but the results I finally got into are shown in the screen over here. And so the graph over here, the value is showing the resolution bandwidth as is reported by the oscilloscope, divided by the calculated resolution bandwidth according to the formula. And we'll assume here that the formula is correct here, and so we're trying to find out whether the scope actually reports the same thing. Now what we see is interesting here, a very complex type of pattern. And then if we start in the left bottom, we basically see here that it starts by reporting only half of the bandwidth than what the formula would tell us to be. Then as we go further, basically he starts to report higher values until we come at a point where the scope is about to switch from 65k points to 32k points. At that point it is still exactly the same as the predicted value, and then it jumps back to only half of it. It grows again. At the moment it would jump from 32k to 16k point. It would drop again to a half, and a number of times that pattern is being repeated, and then basically the last time for the 2002k FFT points, then it goes down, it starts to go up again, and then it even goes much higher, and it doesn't even fit on the graph here. So I also created a graph with a logarithmic scale, and then we exactly see that we get straight lines here. So there's some really strange process going on in the RTB oscilloscope when it comes to the reported value, and on the knowledge that I have right now, I will need to assume that something is going wrong with the reported value, because I will be assuming that the formula we have that should be correct here, and I think we got the right input to the formula. I think we can actually see the FFT points and the sampling frequency. We can see it really nice from the table of all the values that come out of the device, and I don't really know why it is reporting different values in this process here. So what did we learn from today's exercise? Well, first of all, I think the important thing we learned is that the time domain frequency, as we see it shown on the main screen of the device, is actually also and always so the same frequency used for FFT analysis, regardless of other FFT settings. Now this is an important finding, as I already stressed, because if we're doing FFT, you really want to know the actual FFT frequency, sampling frequency, because otherwise you don't know whether the signals you're seeing are real signals or they might be the result of aliasing. The second thing that we learned is that this number that in earlier videos we've been looking at, and which was called the record length, and which had this value mostly or always, I think when I looked at it, of 131 kilo samples, which nicely is the same as 128K, is not the number of sampling points for the FFT, or the number of FFT points. So I think that number better get ignored altogether. And the second thing we learned today, I think, is that the resolution bandwidth as shown by the oscilloscope does not follow the formula that would normally predict the resolution bandwidth, only at some exceptional situations. And this is still the mystery that is left here. I don't really know where these values come from, but without having further knowledge of it, I think only further input of Rohde and Schwarz could help us to understand what is really going on and why it's showing these values, and perhaps they are actually in error. Okay, that was it for today. I hope you found it useful, and if you did, also check out the other videos I got on my channel, and do subscribe if you like it. Thanks for watching, and see you next time.